All right, we started section 5.1 last time. We looked at addition of integers specifically. We also looked at some absolute value information last time. And we're going to pick up this time with subtraction and see many of the same models that we saw with addition, but with a subtraction sort of flair to it. So to start with, we're going to do a definition of subtraction. There it is. Integer subtraction looks much like whole number subtraction we saw before. Says, for any integers a and b, a minus b is the unique integer n, such that a is equal to b plus n. We've talked about this definition before. It's exactly what we mean when we talk about a student or a child not having to relearn their subtraction facts when they already know their addition facts, at least in the sense of maybe they can't do it fast if they don't do that they can get there, right? If I know that 5 plus 2 is 7, then I know that 7 minus 5 is 2, and 7 minus 2 is 5, those fact family kind of things. And just a notational thing more than anything, when we talk about a minus b, it means the same thing as a plus and negative b. Those are two notations that mean the same thing. All right. Does anybody want markers? I'm going to do those charged field or those models with markers. Okay, again, red and black is what I'm going to use. If you use different colors, just make sure your key reflects what you're using. Okay, and so we're going to take a look at what happens when we have something like this. 5 minus negative 3. This is usually the part where people want to do something like change the two negatives in the middle to a positive. We haven't actually established that fact yet. And it's also assuming that you believe it's true. I know that you've been told forever, minus a negative is a positive, or, negative means a positive, or some version of that. And it is true. But if a child asked you why, and you didn't have a very good justification for it, you would be left with a child maybe not really being quite sure that you were being honest or that you knew what you were talking about, right? Why is minus a negative a positive? Why does it work that way? So I want to actually show you the real reason for the why it works that way by talking about an example. So what we're going to do is we're going to do like last time, we're going to draw a circle, and we're going to put 5 chips in the circle. 5 positive chips. Make it a little bit thicker. Okay, so far I have represented my black is positive, and in a minute here I'm going to do red is negative. So what I really want, and what I did when we were working before, is that when we added things, we just put them into the circle, right? Well, if I'm trying to subtract, it would mean I'm trying to take something out of the circle. And what I'm supposed to be doing is taking out 3 negatives. But there's a problem. What's the problem? There aren't any negatives in there, right? How do I take something out that's simply not there? So the way that we do that is we do that with a fact that we encountered last time, but from a different perspective. The fact was about 0 pairs. We talked about the fact that if we had a positive and a negative, we could actually remove both of them because they're equal to 0. Do you guys remember that? Okay, so we're going to do something. Instead of removing the positive and the negative pair, we're going to insert the positive and the negative pair. If I put in a black dot and a red dot, I haven't changed the value inside the circle. Does that make sense? Can I remove 3 negatives yet? No. There aren't 3 negatives there, so I would do it again. Black dot, red dot. Didn't change the value. Can I remove 3 negatives yet? Not yet, but I can do it one more time. Black dot, red dot. The circle is still equal to 5, isn't it? Right now, there's still only 5 in this circle because those 0 pairs cancel each other out. But now this circle has the ability for me to remove 3 negatives, and I can. So I'm going to take these 3 negatives out. And if I take those 3 negatives out, I'm left with a circle that has how many positives in it? 8, right? I have 8 positive chips still in my circle. And now I have a picture for why 5 minus negative 3 yields 5 plus 3. Because I put in 0 pairs and I removed the 3 negatives. Of course, it works, very similarly for subtraction. For the charged fields model. If you remember, the only difference between the chip model and the charged fields model is the symbols we use. Instead of using black dots and red dots, or black chips and red chips, if we were doing this like in real time, we're using charges, and those charges are pluses and negatives. So a positive 5 would be 5 positives. And I want to remove 3 negatives, but there simply aren't 3 negatives to remove. So I'm going to insert what? 3 0 pairs. So I'm going to put in 3 positives along with their corresponding 3 negatives. Technically, could I put in more than that? I could. Eventually I'd have to simplify them and remove them, so I only really want to put in as much as I have to. And then I'm able to take the 3 negatives and remove them, leaving me with 8 positives. It's good? Very nice. All right, the number line example becomes more interesting with subtraction. It'll be even more interesting next week when we look at, not next week, next class period when we look at multiplication. So for the number line model, what we're wanting to do is, it's very difficult to draw it in a way that's very intuitive, but we can move around sort of physically speaking in a way that is more intuitive. So I'm going to draw my number line model and put my 0 on there, and we're going to be over here at 5. So I've gone from 0 to 5, that's the addition of the 5. And then we know that we are going to go 3 more to get end up at 8. So this is 5, and then I am doing plus 3, right? That's what happens. So I want to walk the desks in class to show you why it works, though. Are you guys with me? Yeah? Okay. So I'm going to move 5 desks. I'm going to start over here. This is why I always use the small numbers, because otherwise I would have not enough desks. So I'm going to go 1, 2, 3, 4, 5. I'm going to run out anyway. The first negative tells me to turn around. That's what subtraction would do. But the second negative tells me I'm going to walk backwards. And what happens when I walk 3 backwards? You're at 8. Okay? So if you want to jot yourself down a note as to what they're doing, physically speaking, like kinesthetically, right, is this first one is to turn around. And the next one is to go backwards. The next negative, I should say. Turn around, walk backwards. Well, if I turn around and walk backwards, I'm still going in the positive direction. I just don't have a good way to draw that on the picture. Agreed? Yeah. So we have to just draw it as though it's addition without a lot more going on. All right, pattern model. We mentioned this pattern model last time. Pattern model works really well when you already have some established facts that you know. If you've already worked with some subtraction facts, for example, you probably would know that 5 minus 2 is 3, and 5 minus 1 would be 4, and 5 minus 0 would be 5, because those are whole number facts, right? You have to establish the pattern. You got to have at least 3 in order to have a pattern. If I'm only looking at 2 things, there's no pattern yet. Okay, you got to have 3 of them. So what do we do next? Well, we keep going with that middle value, the one right through here, decreasing every time. So I have 5 minus negative 1, 5 minus negative 2, until I get to where I want to be, 5 minus negative 3. Again, remember the point of what we're doing is not a method. This isn't like the algorithm we do this for all the time. It's explaining or justifying why something works. And then the pattern, of course, on the right-hand side is that we're increasing by 1 as we go down each time, right? We went from 3 to 4 to 5, and then we have 6, 7, and 8. So again, the pattern justifies why 5 minus negative 3 is 8, as opposed to something different. Why does that become plus? Well, the pattern established it. Okay? All right, last topic in this section, this is a really short section as you can tell, this portion of it, is to take a look at order of operations. So, help me out here. What do you remember P stands for order of operations? Parentheses, you got it. What is the E? Exponent. Now, let me pause for a moment to make a mention of parentheses. When we say parentheses, what we mean is what's happening inside of a set of parentheses. It doesn't mean we're eliminating a parenthesis or we're trying to operate on it, to make it go away. That's not what we're doing. We're just simply simplifying inside if it has the ability to do so. Exponents is second. M and D are together on this line. What are M and D standing for? Yep, this is multiplication and division. Now here's the deal. There's really not an order between these two. I know it says MD in this order the way that it's written, but it could just as easily have said DM and would be equally true. So what do we actually do when we get to multiplication and division in our problem? We move from left to right. Okay, so if the division from moving from left to right comes before the multiplication, then we divide first. All right? And the same thing's true for my A and my S. What does A and S stand for? Yep, addition and subtraction. And again, there is no order between these two. I really don't have to add before I subtract. Okay? So, like, instead of saying PEMDAS, it really could say PEDSMA. PEDMSA. I can't even say it right. Like, this is legit. There is no order between the addition and subtraction that says addition has to happen before subtraction. So, whoops, what you do need to know, though, again, is that you go from left to right. So, there's an example in your notes, and they like to ask the question, if I remember right, what is your last step, or what is the step you do last? So we're going to work the problem out and then figure out how to answer that question in a way that makes sense. So looking at this problem, we're going down our list. Do I have parentheses? Nope. Do I have exponents? Nope. So I'm down to the multiplication division step. What would I do first? I would do the 6 divided by 2 because it comes before the multiplication if I move from left to right. So I have 5 minus 2 plus 3 times 4. What would I do next? 3 times 4. And what is 3 times 4? 12. Okay? I did all the multiplication and division. What would I do next? Yeah, the subtraction because it comes before the addition. What is 5 minus 2? 3. And then 3 plus 12 would be 15. So there's two ways to answer the what's your last step kind of question that your book likes to ask. You can either say you add 12 or you add 3 plus 12, right? That's our last step, is to add those two together. Or you could simply say that, well, actually the way I've written is all I want to say. That'll work. Your last step, the thing you do last is actually to add these together. So it's not asking you just to write addition. Sometimes I have people tell me, my last step's addition. Okay, but addition of what? Do you see what I'm saying? It's addition of 3 and 12, or at least, or adding the 12 to the 3 or something like that. Okay, so that's my last step. My answer to this, of course, is 15. My last step that I did was 3 plus 12. Any questions on that?